Good evening. I'll be starting my Module 3 presentation now. I wanted to hold up my hand calculations to start. This is ANOVA. If you can't see them clearly, I will gladly upload them, scanned, email them to you. But now I will screen share with you and show you my presentation in R. I'll start by talking briefly about the general linear model. This is it. Y equals bx plus e, where it looks like the equation for a line because it is a line. Y is the dependent variable, or the outcome. B is a weight that's associated with our predictors, which is represented by x, and E is the error, or residual. So I'll run both multiple regression correlation and ANOVA, which are both like submodels of the general linear model. They have some similarities and differences. I'll start with MRC. And I'm doing this to explore the relationships between the predictors and the criterion. The predictors in this case are x1, x2, and x3, predicting y1. And you can see that here in my model. y1 is predicted by x1 or x2 or x3. And so MRC has these Gauss-Markov assumptions here. There's 9 of them. I'm not going to talk about all of them, but I will probably reference some of them. There's no probably about it. I definitely will reference some of them as I go through my presentation here. So we'll run that model, and I'll put some summary, and we get this where here is our y-intercept. That's where our line crosses the y-axis at minus 0.08. And these are the b values that are associated with the x values. Accordingly, we have a t-value for each one, which is calculated by the standard error divided by the b values here. And that gives us a t-value, or I'm sorry, that was our t-value. And so then we find the significance. None of these are significant. We don't have any t-values. They're significant at the 0.05 level. One's close, but doesn't count. So we would reject the null that any of our predictors are significant predictors for y1. Down here, we have our regression coefficient, which is the shared variance in all of our predictors. And run plots of these residuals. So here we have our fitted values to our residuals. We want this as close to 0 as we can get it, because this is the normal distribution around, or this is the limited variance of our residuals to zeros, because we want variance as close to 0 as we can. No variance would be optimal, but of course that's unrealistic. Next, we have our QQ plot, which this line represents the normal distribution of our errors. 14's looking kind of out of place, and we would want this line to fit. We would want our observations to fit exactly on the line, our residuals. Next, this is our standardized residuals. This looks for, we don't want any of our residuals to Yes, we want our expected error for each predictor to be close to 0, as close to 0 as we can get in an ideal world. So this represents that in the standardization, in the standardized form. And next we have Cook's distance, which shows the leverage of some of our observations, and 14 is having significant leverage on our data. It's pulling, you can see the line pulling it, and you can tell that by the Cook's distance dash line indicator. I want to talk about correlations. So I correlate all the predictors because this would indicate multicollinearity. We don't want multicollinearity in our model. This is one case where it makes sense to compare our predictors or compare our variables, but I want to mention Gary King, who had written in his article that it doesn't make sense to compare variables that don't have a common unit of measure. Like apples and oranges don't compare, even if they're standardized. But here it makes sense because one, we don't have a unit of measure, so we assume it's the same. And two, we're just looking for any collinearity. And when we run it, I find that x1 and x3 are correlated pretty high at 0.67. So to confirm that, we run a variance inflation factor function, and that outputs the VIF, which, surprise, surprise, x1 and x3 have a high variance inflation, something greater than 1. We would want it ideally to be close to 1, like x2 is. So this might indicate that we have multicollinearity for x1 and x3, and that might explain why our results are non-significant. And if we were to remove those confounded variables, it might help us to explain the dependent variable. Moving on to ANOVA. Why do we do it? We do it to observe the differences between our factorial predictors. For this, I used F1 and F2, so we're comparing those. And I mentioned some similarities that ANOVA has with MRC. Some of the assumptions are similar. There's a handy acronym, IID, and they're listed here. I'll refer to some of those as I run through the rest of this. Here's our model again, Y predicted by F1 and F2. And when we run the ANOVA, we get this output here. And we can see here our F1 is not significant at the 0.5 level, and F2 is significant at the 0.03 level. And this was found from the F value. So a high F value gives us a significant p-value, and low F value is the opposite. And the F value is found by taking the between mean squares and dividing it by the within mean squares, indicated by the residual row right here. So Cortina talks about in one article that I had read about removing or retaining factors, and reasons to retain or remove factors might be for subjective reasoning or subjective reasons, just by looking through and deciding which one doesn't fit. That's the least scientific method. Parallel analysis, and then theoretical reasons. So like there might be a theory already established that F2 is the cause or the reason for Y1 or the effect of Y1. And F1 would then be dropped for theoretical reasons, besides the fact that it is not significant. So plot this. Again, we have fitted values versus our residuals, and we want them to be close to 0. And this is a little different in, you'll see the data is stacked like this instead of scattered so much like in multiple regression. And that's because the data is categorical. But other than that, they indicate similar things. So got that one. Here's our normal distribution of residuals. So that's the D of our assumptions. They look fairly normally distributed. And you can see that in other plots too. For example, you can see here, well, no, this is not around 0. This shows at one end of our data, the 1.0, there's a pull negative down low. Those residuals are close to 0, which might indicate some heteroscedasticity, but nothing big or sphericity. And again, here's leverage Cook's distance. And you can see there's not much in here. There's not many observations that look like they have real pull on the data here. And this is where I talked about the distribution. If you drew a curve here, you would find that these are normally distributed, for the most part, pretty close to a normal distribution. So I'll make 2 conclusions from this. F2 is a significant predictor for Y1, as seen here. And from the diagnostics that we might have some heteroscedasticity, but not very much. That concludes my presentation. I hope that you enjoyed it. I'll stop my screen share now. There it goes. I hope that you've enjoyed my presentation, and I hope to hear your feedback soon. Thank you.